Requirements of ASTM C33 or AASHTOM 6-M43 permit a relatively wide range in fine aggregate gradation, but specifications by other organizations are sometimes more restrictive. Fine aggregate grading within the limits of ASTM C33 is generally satisfactory for most concretes. The ASTM C33 limits with respect to sieve size are shown here. Other requirements of ASTM C33 for fine aggregates include: the fine aggregate must not have more than 45% retained between any two consecutive standard sieves. The fineness module must be not less than 2.3 or more than 3.1, and not vary more than 0.2 from the average value of the aggregate source being tested. The amounts of fine aggregate passing the number 50 sieve is limited by most specifications to allow 5% to 30% to pass. For hand-finished concrete floors or where a smooth surface texture is desired, fine aggregate with at least 15% passing the number 50 sieve and 3% or more passing the number 100 sieve should be used. The coarse aggregate grading requirements of ASTM C33 permit a wide range of grading and a variety of grading sizes, as shown in this table. The grading for a given maximum size coarse aggregate can be varied over a moderate range without appreciable effect on cement and water requirement of a mixture if the proportion of fine aggregate to total aggregate produces concrete of good workability. The maximum size of coarse aggregate used in concrete has a direct bearing on the economy of concrete. Usually more water and cement is required for small size aggregates than for large sizes, due to an increase in total aggregate surface area. These graphs show that a given water-cement ratio, the amount of cement or water required decreases as the maximum size of coarse aggregate increases. Aggregates of different maximum sizes may give slightly different concrete strengths for the same water-cement ratio. Typically, concrete with a smaller maximum size aggregate will have a higher compressive strength. The terminology used to specify size of coarse aggregate must be chosen carefully. When speaking of an assortment of particle sizes, the size number of the gradation is used. Often there is confusion surrounding the term maximum size of aggregate. The maximum size of an aggregate is the smallest sieve that all of the particular aggregate must pass through. The nominal maximum size of an aggregate is the smallest sieve size through which the major portion of the aggregate must pass, typically 85% to 95% passing. The maximum size of aggregate that can be used generally depends on the size and shape of the concrete member and on the amount of distribution of reinforcing steel. Requirements for limits on nominal maximum size of aggregate particles are covered by ACI 318. Using this illustration, the nominal maximum size of aggregate should not exceed 1/5 the narrowest dimension of a vertical concrete member, 3/4 the clear spacing between reinforcing bars and between the reinforcing bars and forms. Aggregate is sometimes analyzed using the combined grading of fine and coarse aggregate and the proportions they should exist in concrete. This provides a more thorough analysis of how the aggregates will perform in concrete. The effect of a collection of various sized aggregate particles in reducing the total volume of voids is best illustrated in these figures. A single size aggregate results in higher voids. When the two aggregate sizes are combined, the void content is decreased. As several additional sizes are used, a further reduction in voids would occur. The paste requirement for concrete is dictated by the void content of the combined aggregates. In reality, the amount of cement paste required in concrete is somewhat greater than the volume of voids between the aggregates, shown here. The illustration in the left represents coarse aggregates, with all particles in contact. The illustration on the right represents the dispersal of aggregates in a matrix of paste. The amount of paste necessary is greater than the void content in order to provide workability to the concrete. The actual amount is also influenced by the cohesiveness of the paste. This graph illustrates a theoretical idea: uniform gradation, well-graded aggregate. Well-graded aggregate, having a balanced variety of sizes, maximizes the aggregate volume to the greatest extent. Concrete mixtures that are well graded generally will have less shrinkage and permeability, and be more economical. The combined gradation can be used to better control workability, pumpability, shrinkage, and other properties of concrete. Studies on air-entrained concrete found that the water-cement ratio could be reduced by over 8% using combined aggregate gradation. In gap-graded aggregates, certain particle sizes are intentionally omitted. Typical gap-graded aggregates consist of only one size of coarse aggregate, with all the particles of fine aggregate able to pass through the voids, and the compact coarse aggregate. Gap-graded mixtures are used in architectural concrete to obtain uniform textures and exposed aggregate finishes. They are also used in pervious concrete mixtures to improve stormwater management. Care must be taken in choosing the percentage of fine aggregates in a gap-graded mixture. A poor choice can result in concrete that is likely to segregate or honeycomb because of an excess of coarse aggregate. Also, concrete with an excess of fine aggregate would have a higher water demand, resulting in higher shrinkage. Fine aggregate content depends upon cement content, type of aggregate, and workability. Segregation of gap-graded mixtures must be prevented by restricting the slump to the lowest value consistent with good consolidation. Because of their low fine aggregate volumes and low water-cement ratios, gap-graded mixtures might be considered unworkable for some cast-in-place construction. When properly proportioned, however, these concretes are readily consolidated with vibration. The fineness module, FM, of either fine, coarse, or combined aggregates according to ASTM C125 are calculated by adding the cumulative percentages by mass retained on each of a specified series of sieves and dividing the sum by 100. The specified sieves for determining FM are number 100, number 50, number 30, number 16, number 8, number 4, 3/8 inch, 3/4 inch, 1/2 inch, 3 inch, 6 inch. Fineness modules is an index of the fineness of an aggregate. In general, the higher the FM, the coarser the aggregate. An example of how the FM of a fine aggregate is determined, with an assumed sieve analysis, is shown in this table. The particle shape and surface texture of aggregate influence the fresh concrete properties more than the properties of hardened concrete. Rough-textured, angular, elongated particles require more water to produce workable concrete than do smooth, rounded, compact aggregates. In turn, aggregate particles that are angular require more cement to maintain the same water-cementing materials ratio. Angular or poor-graded aggregates may also be more difficult to pump. Void contents of compacted fine or coarse aggregate can be used as an index of differences in the shape and texture of the aggregates of the same grading. The bond between cement paste and a given aggregate generally increases as particles change from smooth and round to rough and angular. Flat and elongated aggregate particles should be avoided, or at least limited to about 15% by mass of the total aggregate. A particle is called flat and elongated when the ratio of length to thickness exceeds a specific value. A number of automated test machines are available for rapid determination of the particle size distribution of aggregate. Shown here is a video grader that measures size and shape of an aggregate by using line scan cameras wherein two-dimensional images are constructed from a series of line images. The bulk density or unit weight of an aggregate is the massive weight of the aggregate required to fill a container of a specified unit volume. The volume is occupied by both aggregates and the voids between aggregate particles. The approximate bulk density of aggregate commonly used in normal weight concrete ranges from about 75 pounds per cubic foot to 110 pounds per cubic foot. The void content between particles affects paste requirements in concrete mix design. Void contents range from about 30% to 45% for coarse aggregates to about 40% to 50% for fine aggregate. Angularity increases void content, while large sizes of well-graded or uniform aggregate and improved grading decreases void content. The density of aggregate particles used in mixture proportioning computations is determined by multiplying the relative density of the aggregate times the density of water. Most natural aggregates have particle density of between 150 and 181 pounds per cubic foot. The relative density of an aggregate is the ratio of its mass to the mass of an equal absolute volume of water. Most natural aggregates have relative densities between 2.4 and 2.9, which means that the aggregates are 2.4 to 2.9 times as dense as water. It is used in certain computations for mixture proportioning and control, such as the volume occupied by the aggregate in the absolute volume method of mixed design.